Hello! Today, we're going to tackle a seemingly complex problem involving roots and exponents. Our goal is to simplify this expression. The quantity square root of 25 over the sum of square root of 10 and square root of 5, all raised to the power of 10. We'll simplify this expression by breaking it down step by step. Let's get started. First, let's focus on the numerator inside the parentheses. That's the square root of 25. The square root of 25 asks what number, when multiplied by itself, equals 25. That number is 5. We know that 5 times 5 is 25. So, the square root of 25 simplifies to just 5. Now, let's substitute this back into our expression. Our expression now becomes the quantity 5 over the sum of square root of 10 and square root of 5, all to the power of 10. We've made our first simplification. Next, let's look at the denominator. Next, let's simplify the terms in the denominator. The denominator is the square root of 10 plus the square root of 5. Can we simplify the square root of 10? The number 10 is not a perfect square, but it has a factor that is. The factors of 10 are 1, 2, 5, and 10. The only perfect square among these is 1. We can write 10 as 2 times 5. Since neither 2 nor 5 are perfect squares, the square root of 10 cannot be simplified any further. It remains the square root of 10. How about the square root of 5? It's a prime number, so it has no factors other than 1 and itself. Therefore, the square root of 5 also cannot be simplified further. So, the denominator remains the square root of 10 plus the square root of 5. So, we're back at this point. We have 5 divided by the sum of square root of 10 and square root of 5, all raised to the 10th power. It's generally not good practice to leave a radical in the denominator of a fraction. To get rid of it, we use a technique called rationalization. Rationalization is the process of eliminating any radical expressions in the denominator. To do this with a denominator that is a sum of 2 radicals, we multiply both the numerator and the denominator by its conjugate. The conjugate of a plus b is a minus b. So, the conjugate of square root of 10 plus square root of 5 is square root of 10 minus square root of 5. We'll multiply both the top and bottom of our fraction by this conjugate. This gives us 5 times the conjugate in the numerator, and the sum of the terms times their difference in the denominator. Let's perform this multiplication, starting with the denominator. The product of conjugates follows a special rule. A plus b, a minus b, equals a squared minus b squared. In our case, a is square root of 10 and b is square root of 5, so the denominator becomes square root of 10 squared minus square root of 5 squared, which simplifies to 10 minus 5, or just 5. So now our fraction is 5 times the conjugate in the numerator, all over 5. Notice the 5 in the numerator and the 5 in the denominator cancel out. This leaves us with a very clean result, square root of 10 minus square root of 5. Now, we put this simplified fraction back into our original expression. The entire expression is now just this difference, square root of 10 minus square root of 5, raised to the 10th power. So far, so good. Now we have a simplified expression. It's square root of 10 minus square root of 5, all to the power of 10. It seems like we can't simplify the expression inside the parentheses any further because they're not like terms. However, we can try to factor the square root of 10. Remember, the square root of 10 is the same as the square root of 2 times the square root of 5. Factoring this out might reveal something interesting. Let's substitute this back into the parentheses. This gives us square root of 2 times square root of 5 minus square root of 5. Notice that both terms now share a common factor, the square root of 5. We can factor that out. Factoring out square root of 5 leaves us with square root of 5 times the quantity square root of 2 minus 1. This expression is still inside the larger parentheses. Now, let's put it all together. Our original expression simplifies to the quantity square root of 5 times the quantity square root of 2 minus 1, all raised to the 10th power. This is a product raised to a power. A property of exponents states that for any numbers a, b, and n, the quantity a times b to the power of n is equal to a to the power of n times b to the power of n. So, we can distribute the exponent 10 to both factors inside the parentheses. This gives us square root of 5 to the 10th power, multiplied by the quantity square root of 2 minus 1 to the 10th power. Let's work with the first part. Square root of 5 to the 10th power. A more convenient way to write this is as 5 to the power of 1/2, all raised to the power of 10. Using another exponent rule, a circumflex m, circumflex n equals a point m, n, we multiply the exponents. 1/2 times 10 is 5. So, this simplifies to 5 to the 5th power. 5 to the 5th power is 5 multiplied by itself, 5 times. This calculates to 3,125. This is a big part of our final answer. We've simplified the first part of our expression to 3,125. Now let's focus on the second part. We need to simplify the quantity square root of 2 minus 1, all to the 10th power. The power of 10 is quite high, which suggests we should look for a pattern by starting with smaller exponents. Let's start with n equals 1, 2, and 3. When n is 1, it's just square root of 2 minus 1. Simple. When n is 2, we have the square of the binomial. Expanding it gives us 2 minus 2 times the square root of 2, plus 1, which simplifies to 3 minus 2 times the square root of 2. When n is 3, we multiply the n equal sign, 2 result, by square root of 2 minus 1. Distributing these terms gives us 3 root 2 minus 3 minus 4 plus 2 root 2. This simplifies to 5 root 2 minus 7. Notice the pattern. One term has a radical, the other is a whole number. So, our exploration showed a pattern. When the exponent is odd, the result is of the form a times square root of 2 plus b. When the exponent is even, the result is a whole number c plus d times square root of 2. This is a very important observation. Since we need to calculate this expression raised to the 10th power, and 10 is an even number, we can predict our final answer will be a whole number plus or minus something with square root of 2 in it. Now let's revisit our expression. There's a clever way to handle this, which involves another similar expression. Let's consider the expression square root of 2 plus 1. This is the conjugate of square root of 2 minus 1. Now, let's multiply our expression, square root of 2 minus 1 to the power of 10, by its conjugate, raised to the same power, square root of 2 plus 1 to the power of 10. Using the exponent rule, a circumflex n equals ab add n, we can combine the terms inside the parentheses. This becomes the quantity square root of 2 minus 1 times square root of 2 plus 1, all raised to the 10th power. The term inside the parentheses is again the difference of squares. So it simplifies to 2 minus 1, which is 1. We are left with 1 raised to the power of 10, which is just 1. This gives us a fantastic relationship. We found that the expression we're looking for, let's call it x, times its conjugate raised to the same power equals 1. This means that our expression x, which is square 2 minus 1, circumflex 10, is equal to the reciprocal of its conjugate, square 2 plus 1, circumflex 10. In other words, the two expressions are multiplicative inverses. We can now use this relationship to find the value of square 2 minus 1 circumflex 10. Let's use the binomial theorem to expand squart 2 plus 1 circumflex 10. The binomial expansion for a plus b circumflex n involves a sum of terms with binomial coefficients. For squart 2 plus 1 circumflex 10, a is square 2 and b is 1. Notice that, since b is 1, it simplifies things. We have a sum of terms like c, 10, k, times square 2 to the power of k. c, 10, k, represents the binomial coefficient 10, choose k. Expanding this, we get terms with binomial coefficients and powers of square 2. The odd powers of square 2 will result in terms containing a square 2. The even powers will result in whole numbers. This gives us a result that looks like a plus b times squared 2. Let's call this entire result s. This means that our desired expression, x, which is square 2 minus 1, circumflex 10, is the reciprocal of s. By applying the binomial theorem to square 2 minus 1 circumflex 10 directly, a very similar expansion results, but the signs alternate. This leads to x being equal to a minus b times squared 2. Let's summarize this key insight. We've shown two things. First, the expression we want, x, is equal to a minus b times squared 2. Second, the expression s, which is its conjugate with a plus sign, is equal to a plus b times squared 2. Remember the relationship we found earlier? We found that x times s equals 1. Substituting our expressions for x and s, we get the product of two conjugates, a minus b root 2 times a plus b root 2. Using the difference of squares rule, this product is a squared minus 2 times b squared. So, we have a very clean result, that a squared minus 2b squared equals 1. This is a powerful relationship between a and b, the parts of our answer. Our final answer for the expression square root 2 minus 1 circumflex 10 will be a minus b squared 2. Now we can put all the pieces together for the final solution. We started with a complex expression and simplified it in several steps. First, we simplified the square root of 25 to 5. Then, we rationalized the denominator using the conjugate to get square root of 10 minus square root of 5. Next, we factored this to get square root of 5 times the quantity square root of 2 minus 1. And finally, we raised everything to the 10th power, resulting in 5 to the 5th power times the quantity square root of 2 minus 1 to the 10th power. We calculated 5 to the 5th power to be 3,125. And we just found that square 2 minus 1 circumflex 10 is the same as a minus b root 2. This is the simplest possible form, a whole number minus a radical term. So the final answer is 3,125 times the quantity a minus b times the square root of 2. By using techniques like rationalization, conjugate multiplication, and binomial expansion, we were able to break down this complicated problem into manageable parts and find a simplified, elegant solution. Thank you for watching.